The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I will respond as soon as I can. All right, eventually we're going to start chapter 9. But before we do that, I want to talk about a bunch of emails that I received over the last day concerning the test. So quite a few of you made a statement similar to this. I knew the right answer, but I put the wrong answer in WebAssign. Please consider my work. Well, here's the deal, okay? Even though I don't make it mandatory that you attend live these Zoom sessions, you are responsible for the information that is contained within them, which includes descriptions of how to use WebAssign. Also, the whole idea of doing the homework on WebAssign is so that you get used to the process of how WebAssign works. So if you're not sure about something in WebAssign, you should be asking about it, either in one of these class meetings or during my office hour or emailing me and having me get in touch with you. But you are responsible for knowing how WebAssign works before the test happens, especially with graphing. There are specific things you need to do that aren't very intuitive. I explain it fully in my lectures, and yet I'll get students that after the test will say, well, I really didn't know how to graph. Well, my guess is you really didn't watch the videos. So I just wanted to clarify that. Before the test, you're supposed to know how to use WebAssign. You do that by practicing the homework. If you have questions, ask about them before the test, not afterwards. All right. Anyway, moving on. So we're going to go into chapter 9 today, and we're going to be looking at radicals, roots, etc., etc. So let's get started here. What is a root? Well, Marissa, can I ask you a question? Do you mind talking?
Yes, go ahead.
Okay, so if I were to say to you, tell me about your roots, am I asking you about your hair, or what am I asking about?
Probably like since from the beginning.
Yeah, where you came from, you know, where did you grow up? Tell me some of your history. So your roots. So the roots would be like where somebody came from, okay? Let's say I take the number 3, thanks Marissa, and I square it and I get 9. 9 is what we call a square, or in fact, a perfect square. What if I said I want the square root of 9, meaning I want to go back to the number that I squared to get 9, and that would be 3. So in fact, if I had invented it, and instead of calling it a square root, I would have called it the unsquare, okay? We're going to take a number and square it. We're going to unsquare it and get back to its root, back to the thing we started with that we squared to get the square. Okay, I don't know if that makes sense or not, but that's my story and I'm sticking to it. All right, now, so let me put my glasses on here. If we have a positive real number, let's go back to just using 9, and we take the square root of 9, we get 3. 3 is called the positive or the principal square root. Now, I point that out because 3 squared equals 9, but -3, the quantity squared, also equals 9. But when we go back the other direction and we take the square root of 9, we just get the positive or the principal square root. On your calculator, if you take the square root of 9, it shows up as +3, not -3. Okay. Now, the square root of 0 is 0. The square root of a positive number is going to be a positive number. The square root of a negative number, let's say -9, is not a real number. So we say that we can't take the square root of a negative number and get a real answer. Okay. Now, let's take a look at some examples, and we'll come back to some other definitions here in a bit. Hang on here. So let's say we've got the square root of 49. What is the square root of 49? It's whatever number squared is 49, that is whatever positive number squared, so it would be 7. So the square root of 49 is 7. How about, here we go, the square root of 64? Well, that would be 8. What about negative the square root of 64? Well, this square root symbol is a grouping symbol, among other things. So we would do what's inside the square root, and then that would come outside and we'd apply the negative sign. So we can get a negative answer, but only because there's a negative, or like an implied -1 multiplier outside of the square root. Okay. Now, let's talk about the terminology. If I have the square root of 4, this grouping symbol is called a radical. Okay. The quantity inside is called the radicand. Now, let's say I've got the cube root of 8. This is the radical. This is the radicand. This 3 is called the index. All right. The cube root of 8 is the number which cubed is 8. So that would be 2, because 2 times 2 times 2 is 8. Back in this example, there's no index written. In mathematics, when something is fairly common, they'll use special notation or perhaps lack of notation. If there's no index written, it is an implied 2. Since the second root, or the square root, is the most common root taken, math people decided that, well, if we're taking a square root, we just won't bother putting an index there. It'll be an implied 2. Okay, so we've got the index, we've got the radical, and the radicand. Again, the radicand is the stuff inside of that radical, which is a grouping symbol. All right, let's see here. Now, we said that you can't take the square root of a negative number and get a real answer. I'm going to expand that and say you can't take an even root. So a square root, a fourth root, a sixth root. When you take an even root of a positive number, you can't get a negative answer. And you can't take an even root of a negative number. So let's say that this is even, okay? The index is even, all right? And inside we've got the radicand, okay? So the radicand has to be non-negative, either 0 or positive, okay? And the answer has to be non-negative, either 0 or positive, okay? Now, what about odd roots? Let's go back to the cube root of 8. Let's write that a little nicer. The cube root of 8. We said that that was 2 because 2 times 2 times 2 is 8, or 2 cubed is 8. We could even say the cube root of 2 cubed equals 2. But what about the cube root of -8? Now, again, I said you can't take an even root of a negative number and get a real answer. But isn't -2 times -2 times -2 -8? So we can take an odd root of a negative number. And when we do, we can get a negative answer. So the restrictions are with even roots. You can take an odd root of a negative number, you can get a negative answer. But when you take an even root, the radicand has to be non-negative, either 0 or positive, And the answer has to be non-negative, either 0 or positive. And those rules are going to come back to haunt you time and time again if you're not careful. So pay close attention to them. All right, now let's deal with a variable situation. Let's say we've got the square root of x squared. Okay. Now, let's say that x is 5. All right. So what I've got here is the square root of 5 squared, which is the square root of 25, which is 5. Right? Okay. Not a problem. But now let's take a different scenario. Let's say the square root of x, we're going to find the square root of x squared. But in this case, x is a negative number. Okay. Now, first of all, you might say, well, then we can't take the square root of it. Well, yes, we can, because let's say x is -3, for instance. What's -3 squared? It's 9. So we're taking the square root of 9, right? Okay, we can do that. But let's go back up here. We might think the square root of x squared is x. But remember, x is -3, and we can't have a negative answer when we're taking an even root. So if we were to say this, we'd have a problem, right? Because that doesn't work. So what we'd have to do is, take its absolute value, which would make it positive. So then back up here, we take its absolute value. So how does that all work out? Okay, well, let's start over. Let's say I've got the square root of y squared, okay? And I say that y can be any real number, okay? So y could be positive, y could be negative, y could be 0. Well, the square root of y squared is y, except that if y itself is negative, then we're getting an answer that's negative. So what would we have to do? We'd have to say that. Now we're assuring whoever that the answer is non-negative. So we need those absolute value bars in that context. Now, things can get a little bit tricky, and you can try and memorize a whole bunch of special cases. I would just take it a case at a time and think it through. Let me go through that situation with you, and let's see how you do, okay? Let's say I want the square root of 64t squared. And the directions say, simplify each expression. Assume that all variables are unrestricted. Now, what do they mean by unrestricted? They mean that it could be any real number, positive, negative, or 0, okay? Give each answer. So let's see, use absolute value symbols when necessary. All right, the square root of 64 is 8. The square root of t squared is t, but t could be a negative number because then the negative number squared would be positive. But when I just leave t as part of the answer, I have to put absolute value bars around it so that now I know it's not a negative answer. Okay, now another example, square root of 36 y to the 4th. Same instructions, the variables are unrestricted. Well, the square root of 36 is 6. The square root of y to the 4th power is y squared. Now, I don't need absolute value bars on this problem. Why not? Even if y is negative, y squared would be positive, so I don't need to put absolute value bars there. So my answer is just 6y squared. Okay. All right, now, let's see here. Let's separate these examples. What about the square root of 9y to the 6th power? The square root of 9 is 3. The square root of y to the 6th power is y cubed. Do I need absolute value bars here? Yes, I do. Since, again, y is unrestricted, y itself could be negative. Well, y to the 6th power would be positive. But if y is negative, y to the 3rd power would also be negative. So I need absolute value bars there. One more example. The square root of 4 n to the 8th power. Well, the square root of 4 is 2. The square root of n to the 8th would be n to the 4th. Well, if n is negative, n to the 8th power is positive, so we're taking the square root of a positive number. But n to the 4th would also be positive, so I don't need absolute value bars there, okay? And there is a pattern emerging, but I encourage you to just be careful and look at each example and think about it. Well, under these circumstances, could that answer be negative? If it is, and it's not supposed to be, we need to put absolute value bars around the variable. Okay, I want to go back for a minute and look at just using the calculator. Okay, and I'm going to refer to a TI-30X Roman numeral 2. This is an S for solar. And on this calculator, there is a button on the left column that says x squared. And the second function key above that button is a square root symbol. Okay. Now, I want to be careful because there's another button on the calculator that has a little caret, and the second function there is the xth root, okay? And it's kind of hard to see that little x. These are different, okay? Right now, we're going to deal with this one. So if I want to find, let's say, the square root of 340, with my calculator on, I'm going to push the second function key, okay? Then I'm going to push the x squared button, and it's going to access that square root. Okay, so when I do that, I have this. On this particular calculator, it automatically puts a left-hand parentheses to the right of the radical symbol. Then I'm going to type in 340. And then I'm going to close it up with a right-hand parentheses and push equals. And I get 18.439088891. And it would keep going, but I've run out of room on my calculator, so it rounds it off. The instructions say round, let's see, what does it say? Round to 4 decimal places, okay? The 0 would be the 4th decimal place. So I go 1 place to the right, the 8 rounds up, so I'm going to write 18.4391. So if I'm answering to 4 decimal places, I have to go to the 5th decimal place. 5 and above rounds up, 4 and below rounds down. Okay, any questions about that? All righty. Let's see here. Next, it asks us to graph some functions, and I'm going to go to my graphing screen, and hopefully this is working. I had big issues with it the other day. I checked it again this morning. It was working just fine. We'll see what happens. Okay, hopefully it'll be working correctly. All right, here's what we have. It says f of x equals the square root of x, okay? And it says complete each table and then graph the function. And here's the table that is given. Let's see, we've got 5 values there, x and y, 0, 1, 4, 9, 16. Okay. So let's complete the table. To find f of 0, we get the square root of 0, which is 0. To find f of 1, we get the square root of 1, which is 1. f of 4 is the square root of 4, which is 2. F of 9 is the square root of 9, which is 3. And f of 16 is the square root of 16, which is 4. Oops, I forgot to write that in there. Now, over here, let's see, we'll label our scale. 0, 0 is right there. 1, 1 is right there. 4, 2 is there. Let's see, 9 would go out here. 9, 3 is there. 16, 4 is off the grid that I've made there. But let me connect the dots, so to speak. Let's see if I can get a curve that works for that. Let's see here. Yeah. All right, now, but what about the endpoints? For instance, let's go back here. What's happening here and what's happening there? Okay, on the left end of this graph, if I were to extend it to the left, okay, going over here, I would have negative values of x, and I'd be taking the square root of a negative number. So 0 is the smallest x value I could use. So basically the graph starts there. But what about to the right? For instance, I found that f of 16 was 4, which would be off the graph over here. So in fact, what we've got is this. Let's see here. Okay. This graph extends with an arrow to the right. Okay. Now, we're supposed to find the domain and the range of this graph.
I have a
Well,
question.
Yes.
So the dots that we're plotting, which ones are they? The ones that the square root that we got 0, 1, 2, 3, and 4?
You say which points are we plotting?
Yeah, the points that you plotted here on the graph, where are they coming from?
Yes. Well, we've got the x values given and the y values that we calculated. So this first point is 0, 0. The second point is 1, 1. The third point is 4, 2. And then what is it? 9, 3. So yeah, we're plotting the ordered pairs, the inputs that were given combined with the outputs that we're finding. Okay. All right. Sure. Now, so the domain starts at 0, but keeps going. We can get a positive number as big as we want and take its square root. The range also starts at 0 and gets larger. So we don't have any negative values in the domain or the range, do we? All right. Now, I didn't choose these x values. The authors of the textbook did. Why do you think they chose inputs of 0, 1, 4, 9, and 16? Why didn't they use 0, 1, 2, 3, 4, 5 like that? Any ideas? Okay. These numbers are all what are known as perfect squares, or just squares. If you take the square root of a perfect square, you get a nice number. So if I were to use, let's say, 0, 1, 2, 3, 4, the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, but the square root of 2 or the square root of 3 are not nice numbers. They're irrational numbers. For instance, on my calculator, if I do the square root of 2, I get 1.4142135562, and it just keeps going on and on and on. And we could approximate those values to plot them, but by using perfect square inputs and then taking the square root of those, we get nice outputs, which are easy to graph. Okay, now let's take a look at another example. So let's go to a new page and let's graph f of x equals the square root of x minus 1. Now, the minus 1 is not inside of the radical. It is not part of the radicand. It's like an afterthought, okay? And again, we're gonna make a table here, and they've given us specific x values, 0, 1, 4, 9, 16, and over here, 5, 10, 5, -5, -5. Okay, so f of 0 is going to be the square root of 0. Then outside of that, minus 1. Well, the square root of 0 is 0, so 0 minus 1 is -1. So we get 0, -1. Let's see, 0, x is 0, y is -1 would be right there. I accidentally started to plot this point. So let's get rid of that. Okay. If x is 1, f of 1 equals the square root of 1. And then after that, minus 1. Well, the square root of 1 is 1, and 1 minus 1 is 0. So x is 1, y is 0. It's there. Okay. 4. F of 4 equals the square root of 4 minus 1, which is 2, minus 1, which is 1. So when x is 4, y is 1. F of 9 is the square root of 9 minus 1, which is 3, minus 1, which is 2. And we've got what, 9, 2, which is there. F of 16 is the square root of 16 minus 1, which is 4 minus 1, which is 3. But again, the way I've drawn my graph ahead of time, I can't go out there. But consider this. The domain x can't be negative. It could be 0 or greater. So your domain would be 0 or greater. Now, the range, however, so again, we've got this graph doing this. The range starts at -1. Well, let's go back to the previous page for a minute. Okay. Here, the range started at 0, okay, the y value. We just had the square root of x. But here, we've got the square root of x minus 1. So we're going to put in these x values and get the square roots, but then we're going to subtract 1. So all of these values are 1 less than all of those values. So that means this graph is down 1 unit. So that's why my range starts at -1 instead of at 0. Okay. Now, let's take a look at some more graphs. And let's see here. Let's take f of x equals the square root of x plus 6. Okay. It says graph each function, give the domain and range. All right. Now, wouldn't it be nice if I could get y values that were nice numbers like 0, 1, 2, 3, 4, 5, etc. So I want to take a square root and get a nice number. The problem is I'm no longer dealing with the square root of x. If I was dealing with the square root of x, then x would have to be perfect squares, 0, 1, 4, 9, 16, unsquaring them, taking the square roots, I get nice answers. But I've got x plus 6. So let me ask you this. What value of x could I put in? Hang on here, let's change colors. What value of x could I put in there so that I'd be taking the square root of 0, which would give me 0? What value of x would I put there so that ultimately I'd be taking the square root of 0?
0.
No, I want this whole thing to be 0. So what would x have to be so that x plus 6 was 0? How about negative 6? Wouldn't that do it?
Oh,
You see it?
yeah.
Okay. What value of x would I put in here so that x plus 6 would give me, when I took its square root, I would get 1. Well, the square root of 1 is 1, right? So how would I make that equal to 1? What would I put in for x? Negative 5. Because wouldn't negative 5 plus 6 be 1? Let's look at this a different way, okay? All right, let's do this. Let's go back and let's get rid of all this. Let's put in here x plus 6. And let's deal with, first of all, in fact, let's move this over. Okay, let's go back to f of x equals the square root of x. Okay, and let's make this table. And if this is 0, this is 0, 1, 1, 4, 2, 9, 3, 16, 4. Okay, this is like a problem we did earlier. Okay, square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3, etc. Okay, now let's call this g of x. We'll say g of x equals the square root of x plus 6. Okay, and I'm going to make this table x and y 0, 1, 2, 3, 4. Okay, and let's clean this up a little bit. Square root of x. What would I have to do to these x values so that I get the same outputs? The square root of x, we take the square root of x, we get y. Here we're taking the square root of x plus 6, but I want to put x values in here so that what's inside the complete radicand is 0, 1, 4, 9, and 16. What I'm trying to get at is this. Here we've got x plus 6. So I want these x's to be 6 less than these x's to compensate for the fact that we're going to add 6. So let's see if you can follow this. Okay, I know this is kind of complicated. If this x is 0, this one would be 0 minus 6. If this x is 1, this x over here would be 1 minus 6. If this x is 4, this x would be 4 minus 6. If this x is 9, this x would be 9 minus 6. If this x is 16, this x would be 16 minus 6. What I'm getting at is these x values, if they're 6 less than those x values, but then you add 6 to each one before you take its square root, you ultimately get the same y values. Again, You might have to look that over a couple times to get that to sink in. But let's see what the graph looks like. Again, let's label it here. -6, 0, -5, 1, -2, 2, 3, 3, and 10, 4. Okay. How does that graph compare to this graph? Take a look at that. Okay. That was the square root of x. The square root of x plus 6. This graph is shifted to the left 6 units to compensate for the fact that we're going to add 6 inside before we take its square root. Okay. Well, what does that do to the domain and range? The domain is still what? 0. Oh, wait, no, it's not. No, it's not. Since we've got a plus 6 inside of here, x could be -6 to infinity. Again, we're not taking the square root of -6. We're taking the square root of -6 plus 6, which is 0. -6 or -5 plus 6, which is 1, etc. Okay. What about the range? Well, the range is still what? 0 to infinity. So we can have negative values in the domain, but the entire radicand still can't be negative. Okay. And again, I know that's kind of a hard concept to swallow. Let's take a look at something that hopefully will be a little bit easier. Let's see. Trying to find my mouse here. I'm going to go back over to this screen. Okay, which hopefully you can still see. All right. Here we just have f of x equals square root of x plus 12. It doesn't say to graph it, it just says find the domain. Okay, now the radicand has to be 0 or positive. So x plus 12 has to be equal to 0 or greater than, which is positive, greater than 0. So if I take the entire radicand and set it greater than or equal to 0, I'm going to get the domain. That means that my radicand will either be 0 or positive. And again, this is all because I'm taking a second, or just in general, an even root. Well, if I solve this inequality, I get x is greater than or equal to -12. So the domain would be -12 to infinity. Okay. Let's take a look at the one we graphed a minute ago. F of x equals the square root of x plus 6. And when we did that, we got the domain was, what was it? It was greater than or equal to -6, but we got that off the graph. But let's just do this. Let's take the radicand and make it greater than or equal to 0, meaning that it's non-negative. Solve for x, we get x is greater than or equal to -6. All right, let's take a look at this one. Let's say t of a equals the square root of 3a plus 17. Again, I'm taking an even root, so the radicand has to be non-negative, greater than or equal to 0. So I'm going to subtract 17 from both sides, divide both sides by 3. So the domain is going to go from -17/3 to infinity. All right. Any questions about that? Okay, so over the weekend, section 9.1, part 1, we'll also spend time on this on Monday, continuing this section. I'll be back at 1:15 this afternoon with an office hour if you have any questions. Otherwise, have a good weekend, and I'll see you on Monday.
Thank you, you too.
All righty.
Mhm.
Bye now.
Bye.